Space is not cold. This is the first thing one needs to understand. Everything you knew about temperature in space was a lie. When scientists talk about minus 270 degrees outside the spacecraft, they are lying not because they want to deceive, but because they are trying to describe something for which we have no suitable words. There is no temperature in space in the sense we put into this concept. There is no cold and no heat there. There is a void, an absolute ruthless void, in which your body can burn and freeze simultaneously. The paradox is that space is not a refrigerator, but an ideal thermos. A thermos that does not let heat escape. And the main problem of an astronaut is not to keep warm, but not to boil alive from their own heat. Every heartbeat, every breath, every movement generates energy that has nowhere to go. Imagine a furnace that has no chimney. The heat accumulates, 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 and you begin to melt from the inside. This is not science fiction. This is the physics of a vacuum. Physics that turns everything we know about temperature upside down. Before we dive into this story of how the void deceives our ideas of heat and cold, subscribe to the channel and give it a like. That way you won't miss other space paradoxes that we reveal every week. Believe me, discoveries await you ahead that will make you reconsider the most basic things you considered obvious. When humanity first began to dream of space, we imagined it cold, icy. The vast expanses between the stars seemed to us something like an Arctic night, only even more severe. This understanding came from experience. Go up into the mountains, and it gets colder. Go up 10 kilometers into the sky, and the temperature drops to minus 50. The logic was ironclad. The further from the warm Earth, the colder. And space is the limit of distance. That means there must be absolute cold. Writers of the 19th and early 20th centuries described space travel as a struggle against chilling cold. The heroes of novels wrapped themselves in furs, stoked furnaces, struggled with the icing of portholes. When Konstantin Tsiolkovsky and other pioneers of cosmonautics began to calculate the real flight conditions, they also focused on the problem of cold. It seemed obvious that a spaceship needed to be insulated like a house in Siberia. A powerful furnace, thick walls, and insulation were needed. Engineers drew designs of ships with multi-layer cladding and thought about heating systems. And only when the first real calculations of heat transfer in vacuum conditions began did someone notice an oddity. The numbers did not add up. It turned out that a spaceship does not freeze as quickly as an object should freeze at minus 270 degrees. Moreover, calculations showed that a ship on the sunny side of the orbit heats up strongly to temperatures that melt metal. The first engineers of the space era faced this problem like a slap in the face. They were prepared to fight the cold, but they got the threat of overheating. When the Soviet Union was preparing the first satellite for launch, one of the main puzzles was precisely temperature management. A satellite the size of a football, packed with electronics that generated heat. On Earth, this is not a problem. The air carries away excess energy. And in space, Sergei Korolev's engineers struggled with this question. First, they proposed a cooling system with fans. Then someone asked, and what will these fans cool if there is a vacuum around? Air drives air in the void. Absurd. Experiments began with polished surfaces, with coatings, with the shape of the hull. The satellite was polished to a mirror shine not for beauty, but so that it would reflect sunlight and not overheat. When finally, on October 4, 1957, the small metal ball flew into orbit, engineers watched the temperature telemetry with horror. The satellite either heated up to plus 50 or cooled down to minus 30. The temperature swings were insane, but it survived. The electronics worked. The first lesson was learned. Space does not freeze instantly. It fries and freezes alternately depending on where you are relative to the sun. With the first manned flights, the problem worsened. A human is a stove. The body of an adult at rest releases approximately 100 watts of thermal energy. It is like a small light bulb that shines inside you constantly. Under physical load, it is 3 to 4 times more. An astronaut in a spacesuit works, moves, breathes, and all this turns into heat. Where to put this energy? On Earth, it goes into the air. You breathe, exhale warm steam, sweat, evaporation cools the skin. You just stand, and the air around you heats up and rises, carrying away the heat. In space, all this does not work at all. There is no air, no convection, no cooling. Yuri Gagarin spent 108 minutes in orbit. A short flight. The life support system of his ship was simple: a cylinder with oxygen, a carbon dioxide absorber, a fan for air circulation inside the cabin. Cooling went simply through the walls of the ship. Heat from the air was transferred to the metal cladding. That radiated it into space. For 108 minutes, this worked. But when flights began to last for hours, and then days, it became clear. An active cooling system was needed, radiators were needed, circulation of liquid was needed, which collects heat from the instruments and the astronaut's body and transfers it to external panels from where it is radiated into space. The American program of flights to the moon faced a temperature nightmare in full growth. The Apollo ship flew to the moon for 3 days. 3 days in a vacuum, where one side of the ship faces the sun, the other into the darkness. NASA engineers came up with a barbecue mode. The ship slowly rotated around its axis, like a chicken on a spit, so that the heating was distributed evenly and no side overheated to a critical temperature. Without this rotation, the sunny side would have heated up to 120 degrees, and the shadow side would have dropped to minus 170. The metal would have deformed, the seams would have come apart, the ship would have been destroyed from thermal stresses. The astronauts flew to the moon, slowly tumbling in the void. And this rotation was not a whim of the designers, but a condition for survival. When Apollo 13 exploded and the astronauts moved into the lunar module to use it as a lifeboat, one of the critical problems was temperature management. The lunar module was designed for 2 people for 2 days. Now 3 people sat in it, and they had to fly for 4 days. The electronics worked, releasing heat. People breathed, moved, kept warm. The module's cooling system was not designed for such a load. The temperature inside began to rise. The astronauts sweated, took off their clothes, but it did not get easier. Moisture condensed on the cold walls facing the shadow, flowed down in drops. Inside the module, its own microclimate formed. One side warm from the sun and working instruments, the other icy from space cold. Jim Lovell later recalled that they were freezing and sweltering at the same time. Feet icy, back wet with sweat. This was a lesson that temperature in space is not degrees on a thermometer, it is an energy balance that can break at any moment. Let's stop and look into the physics of what is happening. Why does space behave so strangely? Why can't we just say that it is cold there and be done with it? The point is that temperature is a characteristic of matter. Temperature is the movement of atoms and molecules. They move fast, it's hot. Slowly, it's cold. But there is almost no matter in space. A vacuum is not a substance, it is the absence of a substance. Between the Earth and the Moon, on average, there are 5 hydrogen atoms per cubic centimeter. 5 atoms in the volume of a thimble. For comparison, in the same volume of Earth air, there are 25 billion molecules. The difference is monstrous. One can say that there are no atoms in space at all, and it will be almost true. When there is no matter, there is no temperature in the usual sense. These 5 atoms can move very fast. Their temperature can be 1,000 degrees, but they cannot heat you up because there are too few of them. They crash into your skin, transfer their energy, but this energy is negligible. It is as if they were trying to warm you by blowing on you through a straw. You can blow even with glowing air, there will be no use. There is not enough matter to transfer a significant amount of heat. On Earth, we are used to 3 ways of heat transfer. The first is thermal conductivity. You touch a hot mug, and heat passes from it to your hand through direct contact. The atoms of the ceramic vibrate fast, collide with the atoms of your skin, make them vibrate faster. Heat flows from hot to cold directly through the material. In space, this method does not work because there is nothing to contact. You hang in the void. The closest matter is your own spacesuit. The second method is convection. You turn on the heater, it heats the air next to it. Warm air becomes lighter and rises. Cold air sinks down. A flow is formed that mixes the air in the room, spreading heat. The entire atmosphere of the Earth works on convection. Warm air rises over the equator, cold air sinks over the poles. Winds, currents, weather arise. This is all convection, the movement of a substance that carries heat. In space, there is no substance that could move. There is no air, no flows, no convection at all. There remains a third method, radiation. This is the only method of energy transfer that works in a vacuum. Radiation is electromagnetic waves. Light, to put it simply, any object that has a temperature above absolute zero radiates electromagnetic waves. Hot objects radiate visible light. Glowing metal glows red, then yellow, then white. Warm objects radiate infrared waves. This is what thermal imagers see. Cold objects radiate in the radio range. Everything radiates always. This is the only way for an object in a vacuum to give away or receive energy. Imagine a spaceship as a lonely island in an ocean of darkness. The ocean is not cold and not hot. It is empty. The island can glow from the inside, releasing heat, but this heat cannot escape through the water because there is no water. It can only be radiated in the form of light. The hotter the island, the brighter it glows, the more energy it radiates. But if the energy it radiates is less than the energy it receives from the outside, the island continues to heat up. If it is more, it cools down. And everything depends on where the energy comes from and where it goes. In space, the main source of energy is the sun. The sun is a thermonuclear furnace that pours a colossal amount of light into space. This light flies in all directions, and part of it hits your ship. Light carries energy. When it falls on the surface of the ship, the energy is absorbed, turned into heat. The ship heats up. How much it heats up depends on two things: how much light it absorbs and how much heat it radiates back. Black surfaces absorb a lot of light. White and shiny ones little. Black surfaces also radiate heat well. White ones poorly. This is a balance. If your ship is painted black and flies near the sun, it will heat up to temperatures at which lead melts. If it is covered with mirror foil and is in the shadow of the Earth, it will cool down to temperatures at which rubber becomes brittle like glass. That is why spacecraft are wrapped in gold foil, not for beauty. Gold is an excellent reflector of infrared radiation. It does not let heat escape from inside the apparatus, but it also does not let excess heat from outside penetrate inside. This is insulation, but not like on Earth. Earth insulation works due to air that gets stuck in the pores of the material and cannot transfer heat by convection. In space, insulation works by reflecting light. Multi-layer thermal insulation of spaceships is dozens of layers of the thinnest film, between which there is a vacuum. Each layer reflects part of the radiation back. Heat gets stuck between the layers, reflects back and forth, and very slowly seeps out. This is a thermos, an ideal thermos. On Earth, a thermos works due to double walls and a vacuum between them. In space, the entire ship is a thermos because there is a vacuum around it. And this is a problem because the heat generated inside, working instruments, the breathing of people, movement, life, all this heat cannot simply dissipate, it accumulates. Inside, it gets hotter and hotter. If a way to get rid of it is not provided, the crew will boil alive in their own ship. When astronauts go into outer space, they face this paradox face to face. A spacesuit is a small spaceship. Inside it is a person who breathes, moves, works, releases heat. The spacesuit is airtight. There is air inside, a vacuum outside. Heat cannot escape through the vacuum, it gets stuck inside. Imagine that you put on a thermos and began to do heavy physical work. In a minute you will be soaked. In 5 minutes you will start to suffocate from the heat. In 10 minutes you will feel bad. This is precisely why spacesuits are equipped with cooling systems. Under the outer shell of the spacesuit, the astronaut wears a special suit that is all permeated with thin tubes. Cold water circulates through these tubes. The water collects heat from the astronaut's body, carries it away to a small radiator, where the heat is radiated into space. Without this system, going into outer space would turn into torture. The first spacesuits used at the beginning of the space era did not have such active cooling. Astronauts went out for a short time and mostly just endured the heat. Alexei Leonov, the first person to go into outer space, almost died not from cold, but from overheating. His spacesuit swelled in the vacuum, became rigid, immobile. Leonov worked, trying to return to the ship, was covered in sweat, suffocating. The temperature inside the spacesuit rose to a critical level. He almost lost consciousness. If he had not managed to return to the airlock in a few minutes, heat stroke would have killed him faster than any space cold. The International Space Station is a workshop for fighting heat. The station flies in orbit, where one side is always facing the sun, the other into the shadow. Every 90 minutes, the station makes a full revolution around the Earth, passing through day and night. 45 minutes of light, 45 minutes of darkness. In the light, the temperature of the outer cladding rises to plus 120 degrees. In the darkness, it falls to minus 150. These swings of thermal stresses are constant. The metal expands and contracts, the seams work, the structure creaks. But that's only half the trouble. Inside the station, people live and work, 6 to 7 people. Everyone releases heat. Inside, dozens of instruments, computers, and life support systems work. All this produces energy. The total thermal power of the station is several dozen kilowatts. It is like several powerful heaters working constantly. Where to put this heat? On Earth, the station's hull would simply heat the surrounding air. The air would carry away the heat by convection. In space, there is no convection. Heat gets stuck inside. If it is not removed, the temperature inside the station will rise in a few hours to 50 to 60 degrees, and people will begin to die from heat stroke. The solution is radiators, huge panels covered with tubes through which liquid circulates. Ammonia, to be precise. Ammonia collects heat from inside the station and transfers it to the radiators. The radiators radiate this heat into space in the form of infrared light. When you look at the ISS from Earth through a telescope, you can see these radiators, large white panels sticking out to the sides of the main hull. They are always oriented edge-on to the sun so as not to heat up from its light and flat to the cold space to radiate as efficiently as possible. Without these panels, the station could not exist at all. This is not an additional comfort system, it is a condition for survival. Radiators are so important that when one of them was damaged by a meteorite and began to lose ammonia, the astronauts made an emergency spacewalk to repair it. Loss of cooling would have meant the evacuation of the station. The history of the ISS is full of dramatic moments related to temperature. Once, the ammonia circulation system broke. The pumps stopped pumping liquid to the radiators. Heat began to accumulate inside. The temperature crawled up. The crew began to urgently turn off non-essential equipment to reduce heat generation. They turned off scientific instruments, part of the computers, lighting in the modules. They left only life support systems. But even this heat was too much. The temperature inside the living modules rose to 30 degrees, then to 35. The astronauts worked in shorts and t-shirts, covered in sweat, trying to fix the pump. Almost 2 days passed before they were able to restore circulation. When ammonia flowed through the tubes again and the radiator started working, relief reigned inside the station. almost physical. The temperature began to fall. The air became breathable again. The astronauts later joked that in space you are afraid not of freezing, but of boiling. A joke behind which stands a cruel truth. On the shadow side of the orbit, there are also dangers. When the station enters the shadow of the Earth, there is no sunlight. The radiators continue to radiate heat into space, but no new heat from the sun comes in. The outer cladding of the station begins to cool rapidly. The temperature falls. If the radiators worked at full power in the shadow as well, the station could overcool. Therefore, there is a system for regulating the flow of ammonia, valves that shut off part of the tubes when the station is in the shadow, so as not to remove too much heat. The balance is critical. Too much cooling, and the temperature inside the station will fall below zero. Life support systems will begin to freeze. Too little, and in the light the station will overheat. This dance between overheating and overcooling goes on constantly, automatically, every 90 minutes, cycle after cycle, year after year. The astronauts inside do not even notice how finely tuned the system is that keeps them alive. An even more cruel temperature regime is on the moon. The moon has no atmosphere at all. The surface of the moon is direct contact with the vacuum of space. When the sun shines on the lunar surface, it heats up to 120 degrees Celsius. This is the temperature at which water boils. If you could put a pot of water on the lunar soil at noon, the water would boil and instantly evaporate into the vacuum. But when the sun sets, the temperature crashes down. In a few hours, it falls to minus 170 degrees. This is a difference of almost 300 degrees. Nothing like this exists on Earth. Even in the most extreme deserts, where it fries up to plus 50 during the day and freezes down to minus 20 at night, the difference is 7 times smaller. The reason is that on Earth there is an atmosphere. The atmosphere is a blanket. It does not let the surface heat up too much during the day because part of the sunlight is scattered in the air, and does not let it cool down too much at night because the air retains heat heated during the day. The moon is deprived of this blanket. It is naked. When sunlight hits the surface, all the energy goes into the soil. The soil heats up without any protection. When there is no light, the soil radiates heat into the black sky, and nothing prevents this radiation from flying away. Cooling goes at the same speed as heating. The astronauts of the Apollo program stepped onto the moon in special spacesuits that were designed for these extremes. The soles of their boots were multi-layered, with insulation so that the heat of the lunar surface would not burn their feet. But insulation is not ideal. The astronauts felt the heat rising from below when they stood on the sun-drenched soil. Neil Armstrong and Buzz Aldrin spent 2.5 hours on the surface of the moon. All this time, their spacesuits fought the heating. The cooling system worked at full power, pumping water through the tubes, removing heat. Inside the spacesuits, it was cool, almost cold. So intensely did the cooling work. But if the supply of cold water was turned off, the temperature inside the spacesuit would have begun to rise catastrophically fast. The astronauts could not afford long stops. Work was carried out at a pace with an eye on the water reserves for cooling and the battery charge that fed the pumps. When they returned to the lunar module and threw off their spacesuits, both were wet with sweat. Despite the cooling, work on the moon turned out to be much more exhausting than expected, precisely because of the temperature, not because of the cold, but because of the struggle with the heat. A lunar night lasts 14 Earth days, 2 weeks of complete darkness, when the temperature on the surface falls to minus 170. This kills everything. The Soviet lunatics that worked on the moon in the 70s could not survive the night. Their systems were not designed for such cold. Batteries froze, electronics stopped working. Lubricant in the hinges solidified. The lunatics fell asleep for the night and no longer woke up. Engineers tried to come up with ways to keep heat inside the apparatus. They used radioisotope heaters, small capsules with radioactive material that decays and releases heat constantly without electricity. These heaters helped, but not always. Cold 1. The Chinese lunatics working on the moon now are equipped with systems that allow them to fall asleep for the night in a controlled mode. They close solar panels, turn off all systems except heaters, and wait for dawn. When the sun rises again and its light touches the panels, the lunacod slowly warms up, the systems come to life, and work continues. This is like hibernation. The only way to survive the lunar night is to wait it out in a thermal cocoon, not moving, not wasting energy. The problem of a human base on the moon is, primarily, a temperature problem. How to build a dwelling that will withstand differences of 300 degrees. On Earth, a building is built taking climate into account. In Siberia, thick walls, double windows, heating. In the Sahara, light walls that reflect the sun. Thick mud brick walls that slowly heat up during the day and slowly cool down at night, smoothing out the differences. But even the most extreme Earth conditions are incomparable with the moon. A lunar base should be buried under the surface. Lunar soil is an excellent insulator. Under a layer of soil of several meters, the temperature almost does not change. It stays around -30 to 40 degrees constantly. This is cold, but stable. Stability can be used. The base can be heated from the inside, and heat will not escape as quickly as on the surface. But a buried base creates another problem. How to remove heat? If the base is airtight, surrounded by soil, then heat from people and equipment will accumulate inside. Radiators are needed that go to the surface and radiate heat into the sky. These radiators must work in night and in day, regulating the flow of heat so that a comfortable temperature is maintained inside the base. Engineers who design lunar bases think not about how to warm people, but about how not to let them boil in their own juice. The space paradox works here too. Mars presents another set of problems. Mars has an atmosphere, but it is thin, 100 times thinner than Earth's. It is almost nothing, but still not a vacuum. The atmosphere of Mars creates a little convection. When the sun heats the surface, the air also heats up and begins to rise. Weak winds are formed. These winds can carry a little heat, but the effect is minimal. The temperature on Mars is -60 degrees on average. At the equator at noon, it can rise to +20, but at night, it falls to -70. A difference of almost 100 degrees in a day. This is still extreme. A Martian rover must withstand these swings. The rovers working on Mars now, like Perseverance, have thermal regulation systems that include radioisotope generators. These generators not only produce electricity, but also release heat. Heat is used to warm electronics at night when the temperature falls to a critical level. During the day, excess heat is removed through radiators. Martian rovers are autonomous machines that know how to balance between cold and heat without human intervention. The programs that manage their thermal regulation systems are some of the most complex in the apparatus. When people land on Mars, they will face the same problems. A Martian spacesuit must be warmer than a lunar one because on Mars it is colder on average and thinner because the atmosphere creates additional load on the material. The pressure inside the spacesuit must be higher than the Martian atmospheric pressure, otherwise a person will not be able to breathe. This pressure difference blows up the spacesuit, makes it rigid like a balloon. Working in such a spacesuit is hard. Every movement requires effort to bend the inflated sleeves and trouser legs, and every effort is heat that needs to be removed. On Mars, convection is weak, but it exists. A spacesuit can use fans that drive Martian air through a heat exchanger, cooling the system. This will work better than in the vacuum of the moon, but still not efficiently enough. The main cooling will still go through liquid circuits and radiators. Astronauts on Mars will wear the same tubular suits under their spacesuits as on the moon. Without them, work on the surface will turn into torture by heat, despite the fact that it is -60 around. Venus is hell. The temperature on the surface of Venus is 470 degrees. Lead melts. The atmosphere is dense, 90 times denser than Earth's. pressure like at the bottom of the ocean at a depth of a kilometer. Convection exists, but it does not help because all the air is hot. There is no cold place where heat could go. Venus is a planet that got stuck in the greenhouse effect. Carbon dioxide in the atmosphere lets sunlight through to the surface, but does not let infrared radiation, which carries heat, go back into space. Heat gets stuck, accumulates, heats up the planet to the state of a molten furnace. Soviet probes that landed on Venus in the 70s and 80s survived on the surface from a few minutes to 2 hours. This is the maximum that the most protected apparatuses could withstand. Electronics melted, batteries exploded, hulls deformed. Not a single cooling system could handle such an onslaught of heat. Venus shows the limit of what happens when the greenhouse effect gets out of control. It is a planet that boiled in its own atmosphere, and it is a warning. Earth could have become the same if the conditions had turned out slightly differently, slightly closer to the sun, slightly more carbon dioxide in the atmosphere, and the greenhouse effect becomes irreversible. Oceans evaporate, water vapor enhances the greenhouse effect, the temperature grows, carbon dioxide is released from rocks, the effect is enhanced even more. This is called a runaway greenhouse effect. Venus is a living example of what this looks like. Let's return to space. Vacuum. Void. The temperature paradox works everywhere where there is no matter that could carry heat. This means it works almost everywhere in the universe. Interstellar space is a vacuum. Between the stars, the distances are so huge that the density of matter drops to a few atoms per cubic meter. This is an even deeper vacuum than between planets. The temperature of interstellar space is about -270 degrees. This is a temperature that is only a few degrees above absolute zero. Absolute zero is -273 degrees Celsius, the temperature at which any molecular movement stops. It cannot be lower. Interstellar space has cooled to this temperature over billions of years after the Big Bang. The universe expands, radiation from the hot beginning stretches out, loses energy, turns into a weak background glow. This is the cosmic microwave background radiation. It permeates all of space, creating a background temperature of -270 degrees. But again, this does not mean that space is cold. It means that the few atoms that are there move slowly. If you find yourself in interstellar space, these atoms will not be able to freeze you because there are too few of them. You will radiate the heat of your body into the void and gradually cool down, but it will take time. Not instantaneous freezing as shown in movies, but a slow fading hour by hour as your body loses heat through radiation. And now imagine an object flying through interstellar space, a spaceship that set off for another star. The star closest to us is Proxima Centauri, 4 light years. Light flies there for 4 years. A ship with people would fly for tens of thousands of years with modern technologies. All this time, the ship is in a deep vacuum, far from any star. The sun behind turns into a bright dot, then fades, becomes just another star in the sky. Almost no light comes from it. There is no source of heat from the outside. The ship cools down. The only heat is what is produced inside. People, instruments, the reactor. If the ship has a nuclear reactor or a thermonuclear engine, it produces a huge amount of heat. This heat needs to be removed. In interstellar space, the only way is radiation. Radiators must be huge. Imagine wings the size of a football field, covered with tubes through which cooling liquid flows. These wings radiate heat into the blackness of space. But the further the ship is from stars, the colder the surrounding space, the more efficiently the radiators work. In a sense, deep space is an ideal place for cooling powerful systems. If we could build a huge computer that releases gigawatts of heat, the best place for it is interstellar space. Their radiators work with maximum efficiency because the temperature difference between the hot radiator and cold space is maximum. But for people, this is a problem. A person cannot live in the cold. Inside the ship, A comfortable temperature of about 20 degrees must be maintained. This means that inside the ship it is warm, outside minus 270. The difference is colossal. Any crack in the cladding, any air leak, and heat begins to escape through radiation much faster. The ship's cladding must be an ideal thermos, multi-layer insulation, vacuum gaps, reflective coatings. And even with this, part of the heat will be constantly lost. One will have to constantly produce new heat to compensate for the losses. A nuclear reactor on such a ship is not only a source of energy for the engines, but also a stove that warms the crew. Turn off the reactor, and the ship will begin to cool slowly. The temperature inside will fall by several degrees a day. In a week, it will be 0 inside. In 2 weeks, minus 20. In a month, the air in the ship will become liquid. Nitrogen liquefies at minus 196 degrees. If it becomes colder inside the ship, the air will literally fall to the floor in the form of a bluish liquid. This is the end. Without air, people will suffocate in minutes. The thermal balance in an interstellar ship is a matter of life and death even more acute than in Earth's orbit. Black holes create their own temperature paradox. A black hole is an object that is so massive that its gravity does not let even light out. Everything that falls into a black hole disappears behind the event horizon and can no longer return. It would seem that a black hole is absolute cold because it does not radiate light. But Stephen Hawking in the 70s showed that this is not so. Black holes radiate. Very weakly, but they radiate. This radiation is called Hawking radiation. It arises due to quantum effects on the event horizon. The vacuum near a black hole is not empty. Pairs of virtual particles are constantly born and disappear in it. Sometimes one particle from a pair falls into the black hole and the other flies away. The particle that flew away carries away energy. The black hole loses mass. This looks as if the black hole were radiating. The smaller the black hole, the stronger this radiation. Large black holes, with a mass of several solar masses, radiate so weakly that their temperature is negligible, billionths of a degree above absolute zero. But small black holes, if they exist, can be hot. A black hole the mass of a mountain would radiate like a star. A black hole the mass of a speck of dust would explode like a thermonuclear bomb. This is a paradox. The coldest object in the universe can be simultaneously the hottest, depending on its size. Neutron stars are another extreme. A neutron star is what remains after the explosion of a massive star. The core collapses under its own weight, shrinks to the size of a city, but retains a mass greater than the sun. The density is monstrous. A teaspoon of neutron star matter weighs 1 billion tons. The surface temperature of a fresh neutron star is about 1,000,000 degrees. It glows with X-rays, but a neutron star is in the vacuum of space. It can give away heat only through radiation, and it radiates. Gradually, slowly, it cools. In 1,000,000 years, the temperature falls to 100,000 degrees. In 100 million years to several thousand. A neutron star cools for billions of years because it has no other way to give away heat. Vacuum is an ideal thermos. It preserves the heat of a neutron star over times comparable to the age of the universe. Let's return to the human, to our place in this temperature paradox. We live on a planet that is in an ideal temperature balance. The Earth receives energy from the sun, about 1,000 watts per square meter on the illuminated side. Part of this energy is reflected back into space. White clouds, ice at the poles, snow, the light surface of the ocean in shallow water. Part is absorbed by dark soil, forests, the ocean. Absorbed energy heats the surface. The surface heats the atmosphere. The atmosphere is mixed by convection, spreading heat from the equator to the poles, from day to night. Oceans also participate. Currents carry warm water from the tropics to moderate latitudes. All this creates the climate. Climate is the temperature balance on a global scale. The Earth radiates back into space exactly as much energy as it receives from the sun. If it radiated less, the planet would heat up. If more, it would cool down. The balance is almost ideal. The average surface temperature of the Earth is about 15 degrees Celsius. This is warm. This is comfortable for life. But this balance is fragile. Greenhouse gases in the atmosphere, carbon dioxide, methane, water vapor work like a blanket. They let sunlight through but delay infrared radiation, which carries heat back into space. The more greenhouse gases, the more heat gets stuck. The Earth heats up until a new balance is established at a higher temperature. Humanity burns fossil fuel, throws carbon dioxide into the atmosphere. The concentration of carbon dioxide grows. The temperature of the planet grows. This is not an instantaneous process. Oceans absorb part of the heat, delaying the heating. But sooner or later, the balance shifts. The average temperature of the planet over the last century has grown by a degree. This sounds non-serious, but 1 degree on a global scale is huge energy. These are melting glaciers, changing weather patterns, shifting climatic zones. The Earth is slowly turning into a warmer version of itself, and this is happening because of the same temperature paradox that works in space. Greenhouse gases make the atmosphere less transparent to infrared radiation. Heat gets stuck as if in a thermos. The Earth becomes slightly more like Venus. Not as extreme, but the vector is the same. The paradox is that in order to keep warm, one needs to learn to give away heat. Spaceships, spacesuits, stations. All this struggles not with cold, but with heat. The main engineering problem of space exploration is to learn to effectively radiate heat into the vacuum. Radiators become critical components. Without them, there are no space flights. When people fly to Mars, there will be a huge thermal regulation system in the ship. Radiators, liquid circuits, pumps, valves, sensors. All this is needed so that the astronauts do not boil in their own ship. The flight will take months. All this time, the cooling system must work flawlessly. Any failure and the temperature inside will begin to grow. The crew will have to reduce activity, turn off equipment, save every watt of heat. If the system fails completely, the crew will have a few days before the heat becomes fatal. This race against time is an attempt to fix the system before the temperature rises too high. On Mars, the first permanent base will face the same problems. Novobratny Proportsy, Mars is colder than Earth. It will be necessary to maintain heat inside the living modules, but there the thermos paradox will work too. If the base is well insulated from the external environment, heat from people and equipment will begin to accumulate. One will have to balance between insulation and cooling. The Martian atmosphere is too thin to effectively remove heat by convection, but dense enough to create problems with thermal insulation. The base must be designed so that in winter it retains heat, and in summer it removes the excess. A Martian year lasts almost 2 Earth years. Summer and winter on Mars are stretched out. Temperature fluctuations are slow but significant. Engineers who will design the first Martian bases will think about temperature as much as about radiation and pressure. These are the 3 pillars on which survival in space stands. Terraforming Mars, the dream of many space enthusiasts, is, in the first place, a temperature task. To make Mars suitable for life, one needs to raise its temperature and increase the density of the atmosphere. Temperature and pressure are connected. If the polar caps of Mars are heated, the carbon dioxide that is frozen there in the form of dry ice will begin to evaporate. The atmosphere will become denser. A dense atmosphere will create a greenhouse effect, which will heat the planet even more. A positive feedback will begin. Theoretically, if this process is started, Mars could become warmer in a few centuries. But how to start it? How to heat the polar caps? A huge amount of energy is needed. Different ideas were proposed. Place giant mirrors in orbit of Mars that focus sunlight on the poles. Bombard the poles with asteroids. The impact energy will evaporate the ice. Install factories on the surface that produce greenhouse gases and throw them into the atmosphere. All this sounds like science fiction, but real physics lies at the base. Managing the temperature of a planet is managing the energy that comes, is absorbed, and is radiated. This is the same temperature paradox, but on a planetary scale. And humanity is already conducting such an experiment on Earth, though not intentionally. We change the composition of the atmosphere, change the heat balance, see what happens. Mars could become an intentional version of this experiment. The temperature paradox of space teaches us the main thing. A void has no temperature. Temperature is a property of matter. A vacuum is not cold and not hot. It is indifferent. It does not take heat away and does not give it. It simply allows objects to radiate or absorb energy. Every object in space is in its own temperature regime, which is determined by the balance between the energy it receives and the energy it radiates. Change this balance, and the temperature will change. Spaceships, stations, spacesuits, all these are artificial systems that try to maintain a balance in conditions where there is no natural balance. This is a constant struggle, an engineering art. Every spacecraft is a small world that regulates its own temperature itself because there is nothing outside that would do it for it. In space, there is no mercy, no automatic comfort that Earth gives us. On Earth, the atmosphere is a blanket and an air conditioner at the same time. It protects against extremes. During the day, it does not let one overheat. At night, it does not let one freeze. Oceans stabilize the climate, storing heat in summer and giving it away in winter. The Earth is a huge, complex, self-regulating system that maintains temperature in a range suitable for life. We take this for granted. We do not think about how fragile this balance is. But when you go out into space, when you look at the Earth from the outside, you realize this is an exception, this is a rarity. A planet on which the temperature does not kill. A planet where you can breathe, walk, live without a spacesuit. There are few such planets in the universe. There may be billions if you count all the stars and all possible planets around them, but in our immediate surroundings in the solar system, there is only one such, Earth. Space shows us that life is balancing on an edge. Too close to the sun and the heat kills. Too far and the cold stops the chemical reactions without which life is impossible. Too thin an atmosphere and temperature swings become extreme. Too dense, and the greenhouse effect turns the planet into a furnace. Earth is in a narrow range where everything works. This is called the habitable zone or the Goldilocks zone. Not too hot, not too cold, just right. We live in this zone, and we are the only known beings in the universe who realize this, who can go beyond this zone, look at the extremes, return and tell about it. Cosmonauts and astronauts who flew into orbit saw the Earth from the outside. They say that this changes perception. The thin blue line of the atmosphere is so fragile, so thin, that it seems as if it could be pierced with a finger. And you realize, here is everything we have. Here is everything that stands between us and the vacuum, between the heat of life and the temperature paradox of space. The temperature paradox is a lesson in humility. Space does not care about us. It is not hostile, but not friendly either. It just is. A void in which the laws of physics operate, indifferent to our needs. If we want to live in space, we need to learn to build our own small Earths. Ships with atmosphere, heat, light, stations with gardens, water, air circulation, spacesuits that protect us from extremes. Every time a person goes into outer space, they take a piece of Earth with them. Air, temperature, pressure, packed in a spacesuit. This is our continuation, our protection. Without it, we cannot exist there. We are too tied to the narrow range of conditions in which we arose. But we are learning to manage temperature, balance energy, build systems that work in a vacuum. Every space mission is an experiment. Every ship is a laboratory where we test whether we can survive far from home, and so far we are managing. So far, technologies allow us to compensate for what space does not give. The future of space exploration is the future of temperature engineering. When we fly to the stars, the ships will be huge thermoses with powerful thermal regulation systems. When we build bases on the Moon and Mars, each will be a small oasis of heat in a cold desert. When we begin to extract resources on asteroids, mines and factories will struggle with overheating from working equipment and the need to preserve heat for people. Temperature will become one of the main parameters that we will control everywhere we find ourselves, because without temperature control, there is no life, no comfort, no possibility to exist. Space does not give a second chance. An error in heat management, and you either freeze or overheat. Both options are fatal. Engineers of the future will be heroes who design systems allowing us to live where life is impossible by definition. But there is also a philosophical side. The temperature paradox of space reminds us that life is an active process. Life cannot simply exist. It must constantly work to maintain itself. Cells in our body constantly produce energy to maintain temperature, synthesize molecules, move. If this production is stopped, the body will cool and die. Life is a struggle against entropy, against the dissipation of energy. In space, this struggle is exposed, becomes visible. Every spaceship is a living system in this sense. It produces energy, maintains order, balances heat flows. Stopping this process means the death of the ship. Systems freeze or overheat. Order is destroyed. The ship turns into a dead metal coffin. Space shows us that life and order require efforts, that the universe by default moves toward chaos, toward equilibrium, toward the background temperature, and that in order to preserve an island of order and life, one needs to constantly work against this current. People have always dreamed of the stars. We looked at the night sky and wanted to be there. When we finally went into space, we faced a reality that turned out to be more complex and harsher than the dream. Space is unromantic. It is technically complex. It requires precision, knowledge, constant attention to details. The temperature paradox is one of these details, but it is critical. Understanding how heat transfer works in a vacuum allowed us to build ships that can fly for months, stations that work for years, spacesuits that protect astronauts in outer space. Without this understanding, we would not have progressed beyond the first short flights. Cosmonautics began with a dream, but continues thanks to physics and engineering. Thanks to the fact that we have learned to manage temperature where it is not in the usual sense. Imagine a distant future. Humanity has settled throughout the solar system. Bases on the Moon extract helium-3 for thermonuclear reactors. Settlements on Mars are slowly terraforming the planet, growing an atmosphere. Stations in the asteroid belt process or build new ships. Around Jupiter's orbit, research missions fly, studying satellites with subsurface oceans. Everywhere where there are people, there are thermal regulation systems. Everywhere energies are balanced. Every settlement is a point of light and heat in the cold void, and they are all connected by an invisible network of understanding how temperature works in space. Engineers on Earth, the Moon, Mars speak one language, the language of heat transfer, radiation, radiators, insulation. This is a common experience, a common challenge. The temperature paradox unites everyone who goes into space because everyone has to fight it. Let's return to the beginning. Space is not cold. This phrase now makes sense. Space is not a place with a temperature. It is a place where temperature is determined only by what you bring with you and what you receive from the outside. Sunlight can fry you, absence of light can freeze you, but space itself, the void between objects, does nothing. It is passive. It waits. And in this passivity is a challenge, because survival depends only on you, on how well you understand physics, how reliable your systems are, how thought out your actions are. Space does not forgive mistakes. An incorrect calculation of the thermal balance, the mission is failed, an incorrect coating on the ship, and it overheats. A broken radiator, and the crew is in danger. Every detail is important, every system is critical. But in this is the beauty. Cosmonautics is a triumph of the human mind. We took the laws of physics that seem hostile and learned to use them. We turned the vacuum from an enemy into a tool. We learned to build thermoses that fly between planets. We created spacesuits that allow walking on the surface of other worlds. We built a station that has been continuously inhabited for more than 2 decades. Despite the extreme conditions outside, this is an achievement. This is a reason for pride. The temperature paradox was an obstacle that seemed insurmountable at the dawn of the space era. Now we know how to deal with it and continue to learn. Each new mission brings new data. Each new ship tests the limits of the possible. We do not know everything, but we know enough to continue. The moon waits. Mars waits. Further, the asteroid belt, the moons of Jupiter, the rings of Saturn, the icy worlds at the edge of the system. All these are places where the temperature paradox manifests differently, where it will be necessary to find new solutions, where engineers of the future will face tasks that we today cannot imagine. But the experience accumulated over decades of space flights will become the foundation. The understanding that space is not cold, but a void, that temperature is a balance, that survival requires active energy management, all this will become the base on which the further exploration of space will be built. We stand at the beginning of the way. Humanity made the first steps beyond the cradle. We learned to fly into orbit, live on stations, walk on the moon. But this is only the beginning. The real exploration of space will require decades, centuries, maybe millennia of work. Each generation will add its contribution. Each generation will solve problems that predecessors could not solve. The temperature paradox is one of these problems. It is solved for Earth's orbit, solved for the moon, is being solved for Mars. But further, in deep space, on the way to other stars, it will arise again and again, and each time we will have to find new ways to deal with it. When you look at the Earth from orbit, you see a planet that glows in the infrared range. It radiates heat into space. This radiation is visible evidence that the Earth is alive, that processes are going on it that produce energy, that there is life there that warms the planet from the inside. Not literally the main heat comes from the sun, but life affects the climate, the composition of the atmosphere, the balance of energy. Earth without life would be different. Maybe slightly colder, maybe with a different atmosphere. Life and temperature are connected inextricably. And when we carry life out into space, we carry out this temperature balance as well. Every spaceship with people on board is a small island of temperature that moves through the void. This is a continuation of the Earth. This is our way to say to space, we are here, we are alive, and we are not going to stop. The temperature paradox of space is not just a technical problem, it is a reminder of who we are. We are beings who arose in very specific conditions: temperature, pressure, air composition. All this must be in a narrow range so that we can live. Space lies beyond this range completely, unconditionally, but we go there anyway because we are curious, because we want to know what is there, because it is in our nature to overcome boundaries. The temperature paradox is one of these boundaries, and we overcome it not because it is easy, but because it is necessary. Because if we want to become a species that lives not only on one planet, we must learn to handle conditions that are not created for us. So, when next time you hear that space is cold, remember, it is not true. Space is not cold. Space is empty. And in this emptiness, there is neither heat nor cold. Only the law of conservation of energy, which does not forgive mistakes. Space is a place where one needs to create one's own climate oneself, where one needs to balance on the edge between overheating and freezing, where survival depends on engineering, on knowledge, on the skill to manage what is not visible. Heat is not visible. Infrared rays that carry energy are invisible to the eye, but they determine everything. They determine whether you will survive or not. They determine whether you will be able to return home. They determine the future of our species in space. And in this may be the main lesson of the temperature paradox. Space teaches us not to take anything for granted. Every breath on Earth is a gift of the atmosphere. Every warm day is a result of a balance of energies that could easily break. We live on a planet that takes care of us, though not intentionally, that creates conditions in which we can exist. When we leave it, we realize how rare it is, how valuable it is, and how much we must cherish what we have. Because there, beyond the atmosphere, there is nothing like it, only void and a temperature paradox that says, if you want to live here, you must create your own world. You must carry with you heat, light, air. You must become a planet for yourself. The icy breath of the vacuum is a metaphor. A vacuum does not breathe, but it takes away. It takes away heat through radiation slowly, inexorably, if you do not know how to hold it. And it gives heat when the sun shines without the protection of the atmosphere. This is duality. This is a paradox. And this is a reality with which we will live until we learn to change planets, until we build domes and cities under the protection of an artificial atmosphere, until we become a civilization for which space is home. And meanwhile, we are learning, step by step, mission by mission, ship by ship. We are learning to manage temperature there where it is not. And this is one of the most important skills that we will need for the future among the stars. If this story about the paradox of temperature in space made you look at space differently, give it a like and subscribe to the channel. We will continue to explore what is hidden behind habitual phrases and obvious truths. Space is full of paradoxes, and each of them opens a new facet of reality that we are only beginning to understand.